For several years, researchers in human-computer interaction and education have applied augmented reality in learning settings and identified many potentials. Existing literature, such as Radu et al. 2012, has identified 3 potential benefits of AR. Aligned representations present learning contents in 3D spaces and provide better contextualization. Transformed representations enhance original representations with more media forms, visualize the invisible, and reduce cognitive load. Embodiment encourages learners to physically and tangibly interact with the learning content. Prior research also found that AR could contribute to spatial thinking. Most studies use AR to provide multiple perspectives and support the manipulation of virtual objects. Some studies use AR to encourage spatial exploration, which is defined as exploratory behaviors during children's construction of spatial knowledge. Previously, this was primarily achieved through projection-based AR because it can augment larger spaces for children to explore. Yet, projection-based AR is challenging to set up. Often, researchers or practitioners have to go through laborious calibration processes to ensure the alignment between the digital and physical worlds. Marker-based AR is easier to set up, but less connected with the physical world. Hence, prior studies found that marker-based AR often led to users' content-centric movement patterns and less spatial exploration. Fortunately, recent technological advances in room-scale AR have opened new design opportunities. Some devices, such as Microsoft HoloLens, Apple Vision Pro, and some iOS devices, can transform real-world information into room-scale spatial data, such as the dimensions of rooms and certain objects. Through the 3D reconstruction process, it is now possible to dynamically align the digital and physical worlds. However, our knowledge is still limited in terms of how designers can leverage room-scale spatial data to create spatial and embodied learning opportunities. How can we design room-scale AR authoring tools for children's spatial learning? To answer this question, we will first present NetLogo AR, our design for children to author room-scale AR experiences. Then, we will present our empirical findings with young children. Finally, we will discuss design implications for spatial learning. NetLogo AR is based on NetLogo, an agent-based programming language widely used in K-12 education for computational modeling and creative expression. It is spatial in nature. For example, the ants in this model try to find food in a 2-dimensional world. NetLogo is also used for creative expression, enabling children to develop multi-agent games and procedural arts. NetLogo AR is a spatial authoring toolkit that brings NetLogo to the physical world. It currently supports 3 modalities. In room-scale AR, the virtual world is projected inside a room, and the NetLogo program has information about its spatial properties. For example, in the first figure, the ants know where the chairs are and cannot move into them. In plane-based AR, we project the virtual world on a real-world plane, such as a window, a wall, or a table. In non-AR, we represent the real world in a map-like pattern. In the third figure, each colorful block represents a real-world object, and each line a wall. Our design has 3 objectives. First, we aim to encourage spatial exploration. A recent design framework informed us that markerless AR would generate spatial exploration behaviors, so we adopted markerless AR in room scale and plane-based modalities. Second, authoring spatial AR is known to be challenging. For children to author AR content, we leverage the idea of body synchronicity. We are inspired by the logo language, where children position themselves as turtles and imagine how they move in the virtual space. We did the same thing here, but in the physical space. Finally, we also want to support children's spatial thinking. By an easy switch design that instantly converts between AR and non-AR, we hope children will see the connection between the map and the real world, which is known to be difficult in literature. Since NetLogo has been successfully used by young children, we designed a dedicated AR extension that matches the existing NetLogo grammar. Replacing existing code with AR code can easily transform a NetLogo program into a NetLogo AR program. Due to the time constraints, We are not going into details here. The extension and example codes are open-sourced. Please refer to our paper for more information. In spring 2023, after we finished the first prototype, we collaborated with a pre-K-12 social enterprise school in the US, Midwestern area to improve it. 4 researchers conducted 8 participatory design sessions with 7 children aged 11 to 13 and 1 facilitator. For each session, 5 children voluntarily wore a GoPro camera. We collected 48 hours of video data and analyzed it with iterative grounded coding. In the first 2 sessions, we introduced NetLogo AR and invited children to explore together. In the third session, children developed individual project ideas and communicated with researchers. After that, the children spent another 3 sessions working on their projects with our help. The last session was a final showcase. Throughout the process, children served as design informants for NetLogo AR, while researchers served as design informants for children's projects. What did we find about children's engagement with NetLogo AR? Today, we will only present part of our findings. Children were so excited to explore room-scale AR that they initiated multiple rounds of sense-making activities. Most of them grounded their projects in physical spaces. During playing, ideation, and iteration of their projects, they engaged in many spatial thinking activities. Children expressed interest in room-scale AR through their body gestures and visual cues. They often asked questions and repeatedly scanned rooms. For example, in the following episode, Adam was holding an iPad. The iPad was then projected on a screen for others to see. When the facilitators asked, "What is happening here?" Michael stood up from his chair and walked closer to the projected screen with his eyes fixed on it. Sophia audibly drew her breath and murmured, "It's making our room." Children were particularly curious whether AI could recognize their bodies as still objects. Over the first 4 sessions, they initiated 9 collaborative investigations to understand how room-scale AR works. Here the figure shows 3 scenes of such investigations. In each scene, one child held an iPad, and other children attempted different ways to blend in with the environment. Children gradually formed more complex hypotheses. In Scene A, they thought the technology was capturing non-moving objects. In Scene C, they actively tried to blend in with the furniture. The children's enthusiasm for AR's spatial properties did not stop there. 5 out of 6 children grounded their initial design ideas in physical spaces. In the left figure, Michael extended the ants' AR model to have 2 groups fighting for food. The player becomes a super ant that leads their team towards victory. In the right figure, Sophia designed a treasure hunt that requires players to find their way around a series of laser beams. Throughout the playing, ideation, and iteration activities, many children engaged in spatial thinking activities. Here, we use the National Research Council's definition of 3 spatial thinking functions. First is a descriptive function, where people capture and preserve the appearance of and relationships among objects and then convey them to others. Second, an analytic function, where people transform spatial information into relational representations. And third, an inferential function, where people make answers for the evolution and function of spatial objects. We illustrate children's spatial thinking engagement with 3 episodes. The first one happened when they were playing. Vihan, Sullivan, and Adam played with the ants' 8R model we provided. They walked around the room but could not find any digital ants. After a while, Vihan switched to the non-8R mode and saw ants there. He switched back but still could not find any ants. So he switched again, and this time, Adam noticed, "Oh wait, they are in the other room." The 3 moved to the other room and find the ants. From this very brief exchange, we could see the analytical and inferential function happening, as the 3 children collaboratively made sense of the map and the augmented real world and made the decision based on what they knew. In the second episode, Sophia communicated her design idea to a researcher. She first drew a top-down view of the ants' 8R model, which she had seen earlier. When she started to explain her idea, she drew the second, oblique view of the room. Then, she added the spatial placement of lasers, the deactivation button, and the treasure as the little gem. It is clear that she was using the descriptive function throughout the whole process. In the final episode, Adam built on Sophia's prototype. Adam wanted a penalty if the player lost the game. He drew this figure and communicated it to a researcher. He wants to reset the player's location so they can start from the beginning. But there was a problem, Adam said, while pointing to the room. The problem with teleporting yourself back is that it will mess up the 8R. The player needs to move in sync. The teleporting won't actually work. Here, Adam used all three functions of spatial thinking. He described the situation with figures and body gestures. He analyzed the situation and inferred what was going to happen. Finally, he came up with a new idea that the player needs to go back to the starting position. The game would freeze in the meantime. So, we have concluded our findings, and let's return to our research goal. How can we design room-scale authoring tools for children's spatial learning? During playing, iteration, and ideation, children engaged in all sorts of spatial thinking activities. To make sense of the augmented world and design one of their own, children used all three functions: descriptive, analytical, and inferential. So, that is the first step toward our question. However, we also want to know how technology and activity design could contribute to this process. Based on our findings, we propose 4 moments designers could pay attention to. The first is when children have an incentive to find 8R content. Instead of showing them up front, they have to figure it out themselves, so exploring the space is necessary. The second is when they have an incentive to navigate their physical movement based on what is happening in the 8R world. The third is when they have an incentive to communicate their spatial design. Since they cannot draw the 3D world directly on paper, children will need to use and improve their descriptive skills. Finally, when children are incentivized to design around the alignment or misalignment between the digital and physical worlds, there are also opportunities for spatial thinking to emerge. Our study suggests that room-scale 8R opens opportunities for children's spatial exploration and thinking. However, to achieve this, our technology and activity design needs to actively create opportunities for them to explore and to use or improve their spatial thinking skills. For example, by designing and playing with spatial 8R experiences, children in our study engaged with spatial thinking activities. We call for more studies to explore this direction.